We're going to solve this problem now. This is a garden hose attached with a nozzle is used to fill 40-liter bucket. The inner diameter of the hose is 2 centimeter and it reduces to 0.8 centimeter at the nozzle exit. So you see guys here initially let's say at the inlet the diameter was 2 centimeter, and when you see at the nozzle exit it becomes 0.8. So if it takes 50 seconds to fill the bucket with the water, so actually we know actually this 40-liter bucket and it takes 50 seconds to fill the bucket with water. We need to determine the volume and mass flow rate of water through the hose. So we're going to calculate the volume and the mass flow rate, and finally the average velocity of the water at nozzle exit. Alright, so to solve this problem, I believe you understand actually what we're looking for here. Here actually we we need to use a garden hose to fill a water bucket, and here we need to calculate the volume and the mass flow rate and definitely the average velocity at the nozzle exit. Here we'll write down some assumptions. So if I write it down, let's say the assumptions will be, the first one we can say water is a nearly incompressible substance. So water is a nearly incompressible substance. Incompressible substance. So the second assumptions we can say that it is a steady flow. Okay, so the water flow, it is steady. And the third assumptions, like I say, we do not need any third assumptions, so this two should be enough. So what I say, water is incompressible substance, nearly incompressible, and it is a steady flow. So now we need actually the properties, the water properties. Here actually our material is water, so properties, the water, let's say what should be the water density. So density of water, actually we know it is 1000 kg per meter cube. So if we convert it into kg per liter instead of meter cube, then we can say it is 1 kg per liter. So this is we can write. So actually when we will start with this problem, you see guys, look, this garden hose, it is attached with a nozzle and it was used to fill a 40-liter bucket, right? So at first we need to calculate the volume and the mass flow rate. So if we see here, it actually takes 50 seconds to fill that bucket. That means in 50 seconds, okay, so 40 liter of waters are discharged at 50 seconds. So then from the formula, let's say if I write down the analysis, okay, the analysis, we know that actually here we need to calculate the volume flow rate. So the volume flow rate we usually define, it is V bar. So it is equal the volume over delta T. If you see the definition, it should be a small t. So that means the rate of change of volume, it is, or volume flow rate is actually the rate of change of the volume. That means with respect to time. So here the volume flow rate, it will be V bar, it is equal V over T. So in this problem we have the volume is 40 liter and the delta T, it is actually 50 seconds. So in 50 seconds we got 40 liter of the water it discharged. So this is actually the volume, this is actually the second. So if we calculate this, it will be 0.8 liter per second. So this is actually the volume flow rate, 0.8 liter per second. So I think this is very straightforward. We do not need to understand a lot of things. Just if we use the formula, then it should be fine. Now we need to calculate the mass flow rate. You see, the second part of this problem is the mass flow rate. So if we go to a clear slide, then the mass flow rate, we know mass flow rate m bar or m dot, it is equal the density and the volume flow rate. We already discussed all of these theories. So the mass flow rate, it is actually the density and the volume flow rate. So where is the density here? It was previously, if you can remember, I showed you the density is 1000 kg per meter cube or 1 kg per liter. So what we can do here, guys, we can write, let's say it is 1 kg per liter, and this is 0.8 liter per second. So then what we can do, we can cancel out this term L and L, and if we simplify this by using calculator, so 1 and 0.8, so it is 0.8 kg per second. So this is actually the mass flow rate. So we got the answer for the first part of this question. The second part is, you see the average velocity of water at the nozzle exit. So we'll say this is section B. So if we want to calculate the the average velocity of the nozzle exit, so we know the formula. The average velocity, we say, let me write it down this way. The average velocity, it is equal the volume flow rate and the cross-sectional area. That we know the formula. So we already know this volume flow rate, and we don't know the cross-sectional area, AC. So now we need actually AC, the cross-sectional area. And the cross-sectional area of a nozzle, it is pi r square. So this is the cross-sectional area of a nozzle. But here in the question it says the cross-sectional area at the nozzle exit. That means we need to use this r, it is actually radius. We will say the exit, the radius at exit. And if you can remember, in the question it's given the diameter. Let's say if we say this is the nozzle, okay, this is the nozzle, then if we say this is the nozzle, then at inlet the diameter is given 2 centimeter. Here it is 2 centimeter and outlet diameter is 0.8 centimeter. So we all know actually the difference between the diameter and the radius. Here in this formula, this r, it is actually the radius. So we know if it is a circle, if it is the center, so this is called the radius, and this whole, it is called the diameter d. So we can say actually radius r, it is half of the diameter. Okay, so this whole, it is the diameter, and radius is from here to here. So radius, it will be just half of the diameter. So at first, if we want to calculate the the cross-sectional area at the exit of the nozzle, then we need to use this this diameter. So let's say, guys, the cross-sectional area, AC, it is equal pi r squared. We will say it is E, that means the exit. Pi is constant, 3.1416, and here the radius, so it should be I said r equal the diameter over 2, so we can say 0.8 over 2, it is centimeter. So let's say square. So it will be 0.5027 centimeter square. If we convert it into meter, then it will be 0.5027, and centimeter square means we can say it is 10 to the power minus 4 meter square. So this is actually the cross-sectional area, right? This is the cross-sectional area. So once we know this cross-sectional area, then we will substitute the cross-sectional area and the volume flow rate value here, and then we will get actually the average velocity. So now let's move to the next part. So if we say the average velocity, let's say AVG, it is equal to the volume flow rate and the cross-sectional area. So volume flow rate is 0.8 liter per second, and the cross-sectional area is 0.5027 and 10 to the power minus 4 meter square. So if we want to convert it, say this is meter square, so if we want to convert it, the velocity into meter per second, so what we can do, we can just write it like this. Here we actually wanted to convert it into the meter per second, so we just multiply just 1 meter cube here, and we divide 100 liter, 1000, it should be 1000 not 100, so it should be 1000 liter. So actually it will if I show you here, it will eliminate this term L and L, and this meter is and this meter cube, so it should be meter, and it is owned by second, so the final unit, it will be meter per second. So here it will be 15.9 meter per second. So I'm not going to discuss actually this unit a lot because I believe you know it. So here you see the average velocity is 15.9 meter per second. So what we got, guys, at the exit of the nozzle, the average velocity is this. So if in the next quiz, if I give you this same question, and if I ask you what will be the average velocity at the in the hose, okay, what is the average velocity in the garden hose, then can you calculate, guys? So I just keep this question for you, and you just think and see how we can solve this. So this sort of modification you can expect in the final exam or in the next quiz. So here what I did, it is pretty straightforward. We calculated the average, the cross-sectional area, and then we used the formula for average velocity. So I think that's it.